So now we're going to be teaching you the relationships between speed and distance. But first, you know how you've been using the thing d equal to vt. But that is assuming that v is a constant speed. Like the speed is like 3. That is assuming v is a constant speed. But now v is going to be in the changing speed. So it's going to be like 3, and then like 5, and then like 2. So it's going to be changing now. First, what is the relationship between these two curves? If you don't know, we're going to teach you. But first, I'm going to teach you how to read a speed graph. So the speed graph has basically two things. So here, right here, this vertical thing here, that's the velocity, and this here is the time. So to read a speed graph, the first thing you need to do is this. That means it's traveling 1 meter per second, or for 5 seconds, because it's from 0, 1, 2, 3, 4, 5. That goes from 0 to 5 on the time. And then this is traveling 1 meter per second, because it's 0, 1, 2, 3, 4, 5. It's 1 meter per second, and that's traveling for 5 seconds. So that's how to read a speed graph. This is 5 meters per second, because the line is here. It's 5 meters per second for another 5 seconds, because 5 to 10 is 5. And then that is 3 meters per second. 3 meters per second, because 3 is here and that. And that's how you read a speed graph. So now we're going to be learning about a leg. A leg is basically when the speed changes, it makes it look like leg. So an example of leg is like here. There's 3 legs in this speed graph here. The first leg is 1 meter per second. The second leg is 5 meters per second. And the third leg is 3 meters per second. Like that, you can see the 3 legs here. First leg, second leg, and third leg. But now we're going to teach you how to get the distance of each leg. So the first leg is basically just normal thing. D times V1 T. Which is D equal to V1 times T. Or V1 is just a name, it's just the speed. It's just like a speed. That's the distance and that's the time. So to get it, you times the speed by the time. The time is V1 and the time is T. So this equation right here is basically timesing V1 and T to give you a point on this graph. So like an example is, since the first leg is like 1, so V1 is 1. 1 times, let's say you did it for 3 seconds. So you did it for 3 seconds. So it's 1 meter per second. So that's V1. 1 times the time, which is 3 seconds, which is T. So 1 times 3 is 3. So distance equal 3. So it's somewhere, it's here. So the distance when the time equal to 3 is 3. Now for the second leg. The second leg is this thing right here. And to compute the distance for the second leg, you do this equation. D equal to V2. V2 is just a new speed. V2 is just a name. Change anything you want. It's just a new speed than V1. T minus 5 is basically the time from here to there. That is T minus 5. And plus distance 1. Because distance 1 is just here. It's where the other one left off. Is where this leg 1 left off. Distance 1 is from 0 to 5. That is distance 1. And this is just this. So that is how you get the second leg. Now let's do some example. Now the example is, let's say T, the time is 7 and the velocity is 5 because it says right here on the speed graph. So the time, the time is 7, so 7 minus 5 is 2. And then 2 times 5, because the velocity is 5, is 10. So that's 10 distance plus D1. D1 is 5. Because leg 1 is 5. D1 is 5. So 10 plus 5 is 15. So when the time equal to 7, the distance is 15. It should be right here on the distance graph. Now for the third leg is this thing. And to compute the distance for the third leg, you do this equation. T equal to velocity 3. Again, velocity 3 is just a name. You can name it anything you want. T minus 10. T minus 10 is basically the time from here to there. And then plus D2. D2 is this. It's where you left off last time. So like here. Right here. That is D2. Distance 2. So it's like here and that. 10 seconds. So that's how you do it. Let's plug in some numbers so you can see. Let's say this is 14. T is 14. And the velocity is 3 meters per second, as you can see on the speed graph. So 14 minus 10 is 4. And then 4 times 3 is 12. And 12 plus 12. So it's 12 plus 30. 12 plus 30 is 42. So when the time equal to 14, the distance should be 42, which is like somewhere here. That is the thing. So this is basically the summary of what we've done. This means that the distance equal to the velocity 1 times the time. And this T, this means that when the time is less than 5, you do this equation, do this formula. This means when the time is more than 5 but less than 10, you do this one, D equal to V2, velocity 2, T minus 5 plus D2. When the time is less than 5, no, more than 5 but less than 10. And for the third one, you just do this equation when the time is more than 10. That's what this means. And also distance is equal to the sum of the rectangle areas. So let's look at this. So let's say the speed is 1 and then it's 3. 1 times 3 is 3. And to make a rectangle, it's just A times B or something times something. So like 1 times 2 is a rectangle. So this is, you get the distance is actually the rectangle. So look at this. So this rectangle is 1, 5. The time is 5 seconds here, and the speed is 1. So 5 times 1 is 5. That's the distance. But 5 times 1 is also a rectangle. You can see the rectangle here, like this right here. That, we just color it in blue. That is a rectangle. And that is actually the distance, because 1 times 5 is the distance. Because the speed is 1 and the time is 5. That's actually the distance. So the rectangles are actually the distance. Now, as you can see here, this speed graph is broken into many different rectangles. Each one of these rectangles is V times delta T. Delta T just means the changes in time. So like 0 to 1, the changes in time from 0 to 1 is 1. And the velocity here is 1 as well. So the velocity, 1 times the change in delta T, or the change in time, 0 to 1 is 1. 1 times 1 is the area of this rectangle here, which is 1. The area of the rectangle is 1. And the area of the rectangle is equal to the distance. So the distance at time 1 is 1. We can see more clearly if we do this. So now the speed is 5 meters per second. And then the changes in time from 5 to 6 is 1. So you do 1 times 5, because that's the speed, will give you 5. So that's the area of this rectangle right here. And then the area of the rectangle is equal to the distance. So the distance for this, for time 5, is 5. So as you can see here, the rectangles fit perfectly under the speed curve. But sometimes you might get a speed curve like this. The problem with this speed curve is the rectangles can't fit perfectly under the speed curve. There's a little bit poking out. But then we use the equation. A area equals to the limit dt goes to 0, the summative of V of delta t V of t delta t. But that's too long and mathematicians don't want to write that. So the shorter way is a equal to integral. Integral is just the shorter way. It's just a symbol of limit dt goes to 0. Integral phi of t times dt. So that's just the shorter way of writing this. So we use this equation because we want dt to get smaller and smaller. When dt gets smaller, the things poking out will also get smaller. So when dt equals to 0, there will be 0 things poking out. Think, when dt is like 0.1, there will be 0.1 thing poking out. So we want dt to get smaller so we can fit perfectly under the speed curve. So now you know how to do this stuff. Let's get on to coding integration. So now we're going to be doing coding. So the first function here is going to be coding the first leg. So first we do the function distance1, which is just the name of the function. We'll call it distance1 because it's an easy name. So this is basically just the function with the first leg. So here it says the value of v is always 1. And then when you type in this, it says v times t, which is 1 times t. We always give you the distance. So first we type in the distance1 function, and this here, right here, is the time. Because this function already knows when we call it that the velocity will always be 1, because as it says here, value of v equal to 1. So let's do, so if we change this to 1, it will shall give us 1. Let's change this to like 5, it should give us 5. And if let's change to 10 and it will give us 10. This is because this is the first leg and it's just maybe 1 meter per second. Its speed is 1. So this is the distance function, the leg 2. So this function's name is called distance2, but you can obviously name it anything you want. So instead of the value of 1 is now the value of 5. So the speed is now 5. So v times t is now 5 times t. So here the same thing is like we call the distance2 function, and this is the time. Same is the time. So I just type in 6. So it should be 5 times 6, which is 30. And let's just type in a random number like 7. So 7 times 5 is 45. 35, I mean. So this function here, right here, is basically adding the distance1 and the distance2 function. Here it says if t is smaller than t1, which is 5, because it literally says t1 equal to 5 here. So if t is smaller than 5, then you use the distance1 function, which is basically the velocity will be equal to 1. But if it's above 5, if the time is above 5, then you use the distance2 function. This d2, this line basically means that d2 is the distance2 function, which is t minus t1. So here we're just plussing the distance1 function plus the distance2 function, which will give us d12. So this function basically just adds the distance1 function to the distance2 function. So like in the first 5 seconds, let's say we put 3, it will travel 1 meter per second. Like 3, because if we give it 4, it will travel 4. If we give it, let's give it 2, and it'll give us 2. But if we go above 5, like let's say 6, it will give us 10. This is because the first 5 seconds is from second 1, it travels 5 meters. So 1 times 5 is 5, which is the distance for the first 5 seconds, or leg 1. But this is the first 6 seconds and not the first 5. So you need to use the distance2 function, which will add 5 for 1, because it travels 5 meters per second for 1 second. So it adds 5 to the distance, which will equal to 10. Another example of this is we can add here, let's say 8. So here is equal to 20 because the first 5 seconds is 5. But then you plus 15 because it traveled 5 meters for 3 seconds, which is equal to 13. This is equal to 15. Oh, which is equal to 15. Then you do 5 plus 15, which is equal to 20. So what this function does is basically plot the thing on the graph. So here is from point 0 to 10. So at point 0 it should be 1, 2, 3, 4, 5. But at second 6 it should go up to 10. At second 7 it should go up to 15. And second 8, 20. Second 9, 25. And second 10 is 30. We can also see this if we put the thing like here, 10, and it'll give us 10.0. 10, and it'll give us 30. And so this function is basically applying the distance 1, 2 function to the t, which is 0 to 10, which is the point 0 to 10. So now we move on to the distance 3 function, otherwise known as the length 3 function. So the length 3 function is basically the value of v is equal to 3, and you do v times c, similar to the other one, and you return d. So we can try this out. First, we call distance 3. We put a bracket, and we can type a time. Let's say 4.0. You put a bracket, and it'll give you 12 because you times 4 times 3. Let's suppose we change this to 9. It'll give us 27. So this is how that function works. This function right here, though, it adds the distance 1, 2 function to the distance 3 function. So here we can see that the value of t2 is equal to 10. So if t is smaller than t2, then you use the distance 1, 2 function, which is the one up there that we just coded. This one. But if the t is bigger than 10, then we use the d3 function, or it can be written as d3 can be written as distance 3 function, or t minus t2, which is basically the length 3 function. So the value of d1, 2, 3 is equal to distance 1, 2 plus d3, which is return the distance d1, 2, 3. So we can see this function in action by, let's plot the points. Let's type d underscore 1 d underscore, let's write d underscore 1. So short word for distance 1, 2, 3 can be d1 to 3, because I'm not bothered to say d1, 2, 3. So first we put the thing distance 1, 2, 3. So let's just type in distance 1, 2, 3. So here we can see that we put 1 and it'll give us the same thing, just 1. We put like above 1, it'll just give us 20, like the original. But if we put above 10 here, it will actually give us something different. 13, 39. Because now this, let's make it easier so it's easier to see. Let's make it 12. So 36. So we know that the first two is like so the first 5 seconds is 1, 2, 3, 4, 5 because of the distance 1 function. From 5 to 10, it's so it'll be 25. So 5 plus 25 is 30. But the other two, he's traveling for 3 meters for 2 seconds. So you plus an extra 6. This is why we get the total 36. We can make this to the distance 36. We can change this to another number, let's say 11, and it'll be 33 because it's the same thing, but you minus 1 second, so you run 3 seconds less, which is 33. So this function right here, the one below the answer reference d1, 2, 3, is basically just plotting the function. So like 1, 2, 3, 4, 5. And it's also applying the distance 1, 2, 3 function to the points t, 0 to 20. So here we can see 1, 2, 3, 4, 5 as usual, and then we go up to 30, which is It's the same as right here. But now we have a leg 3, which is this leg. So this leg actually goes up to 60, which is the third leg. So to give you the examples, this chart is actually real. As you can see here, is at time 11 is 33, like here. So at time 12 is 36, and at time 13 is 39. So that's how you prove the chart is real. And this thing is basically the speed graph for this distance. So as we saw earlier in the slides, there was a speed graph for the distance graph, and it is this graph. So this basically means if t is smaller than 5, then you need to return 1, always 1. If t is smaller than 10, then you always return 5. And if t is bigger than 10, then you always return 3. This is basically what it means. That's literally all it does. This is just plotting onto a plot. Using Plotly is like a coordinate system, and scatter puts the points in its place. So here we can see that it is the thing. But as you may notice, it doesn't quite match the thing. That's because we used 2 big rectangles. So if we go down here, we can see that we use we only use 20 points, but we can change it to like 200 points. As you can see, it is much more accurate than before. This is because it has smaller rectangles to work with, so it can put smaller rectangles in its place. So if we change it to like 2000, it is not that accurate, but it's a very accurate thing. So let's just change it back to 200 because it's the best one. So now, as you can see, it is way more accurate than before. So after we explain this function, we'll go on to this function. So this function has 3 values of v. Speed, which is velocity or speed is the same thing, but velocity is just a fancy word of it, so we'll use that. So the first value of velocity is 1, the second one is 5, and the third one is 3. This means whenever the time hits 5, then it'll use the second velocity, and when the time hits 10, it'll use the third velocity here. This means if t is smaller than 5, then you do the v1 velocity times the time. If t is smaller than 10, then use the v1 times time plus the second velocity times t2 minus t minus t2. If it's bigger than 10, then you do the first velocity times t2 plus the second velocity times t3 minus t2 plus the third velocity times t3 minus t2. These t3 minus t2 is basically just the leg, like leg 2 and leg 3. So now we're going to be teaching you how to do the integration. So first we name the function distance 1, 2, 3, b. And you can name it anything you want, but we're just going to use this. And we're going to make a dt1, which means the rectangle's width is going to be 1. This basically stands for, so here we have speed, we don't need this, so we're here. So we're going to have, so dd is a rectangle, so we do dd plus dd plus dd plus dd I times. Because we can't do dd times I because the dd is constantly changing. So we do the total distance plus dd, which will give us 1, 2, 3, b. So when we plot this, we can see that at time 10, it's going to be 32. But it's not very accurate. As you can see, when we did the other method, when time 10 is 30, because that's the most accurate answer. But this one is only 32. Because it's 32 because the rectangle here are too big. So we're going to write this in a different formation, like this. And we're going to change the width of the rectangle to 0.1. Right now, when we go to 10, it's going to be 30.1. That is closer to 30, because we changed the size of the rectangles. We can also change again to 0.01, which will get us even closer to 30. So we can change this to like 0.0000. and let's just change this to 0.01, and it will be even closer than it was. So that's how you compute the